So next, I would like to introduce Wei-han Lien. He is currently leading an architecture team in defining a high-performance RISC-V CPU fabric, system caching, and high-performance memory subsystem for the Tenstorrent heterogeneous high-performance computation platform for AI and HPC computing. The floor is yours.
Hello. Sorry, this topic is slightly different from whatever posted by conference. We had 2 papers accepted, but we are confused. So this is a topic I'm going to present. I hope it's not going to disappoint you. It's going to be equally interesting, right? So what I'm going to talk about is from milliwatt to megawatt. Right? So Tenstorrent actually building a wide range of technology enable us to address the market from wearable device and all the way to high-performance computing. So introduction to our company, Tenstorrent, and then our product roadmap. And then I will talk about how important RISC-V is, right, to enable our AI processor product. And then I will talk about another project I'm leading on is that RISC-V high-performance processor family. And then I will talk about the chiplet strategy we've been using for scale the system now. Tenstorrent actually founded in 2016. At the end of the company is actually building the best machine learning processor for inference and training. Our CEO is Jim Keller, right? Has tremendous, delivery, great record on delivering the chip on the alpha processor, right? Digital alpha processor, and then also the Apple A series processor, and the AMD Zen processor, and then Tesla autonomous driving system. And the company actually raised $230 million so far with the 300 employees, right? Geographic distributed around the world. We will have 2 machine learning chips, right? One is called Grayskull, the other is Wei-han in production. We are working on the third to tape out. And then I joined 2011, so we are building a high-performance RISC-V processor for the data center. So we think we are the only company positioned, right, in the world has the high-performance RISC-V processor technology and also the mature machine learning technology for training and inference. So this is our AI chip product roadmap. So as I mentioned before, we will have 2 chips coming back, Grayskull and Wei-han, right? So you see there's a board there. Right, so the first version, Grayskull is a PCIe card-based, right, 12 nanometer. And the second generation is basically a derivative from the first generation. So what it has is actually has this Ethernet port and talk with the Rocky, right, so that you can scale out to the system so you can using the multiple of those chips, right, building a much larger system. Right. And then 2023, that's when we start introducing heterogeneous compute to our system. So we are taking out this black hole, we start integrating the Sci-Fi XB280, right, into our system, so that become a heterogeneous compute with the AI and also general purpose compute. Right. So starting on 2024, the company is shifting the strategy to the chiplet. Right. Chiplets actually enable you to have the composable element much more flexible for you to actually form a much high performance computing system with only the package design, right? Not the whole redesign the whole chip. So this is the strategy company is focused on. As you can see, there's a Quasar, which is a chiplet based, right, machine learning processor. And then we are working on this 128 core high-end Zen 4, Zen 5 level Ascalon processor based, right, chiplet, which will be a companion processor. And then we were coming out with this next generation NVIDIA next generation Gray Hopper competitor with this kind of strategy. So, so when we talk about scalability, right, our architecture is actually very scalable, from all the way from machine learning to general purpose processor. And you can see here, our first generation Grayskull has this T cell, right, in there. It's actually a 10-6 element we call. And then the whole system is actually composed together, right, with this 10-6 core with the 2D torus connected NOC, right. Inside this 10-6 core, starting 2016, we already utilized the RISC-V as an embedded processor in there. So there are 5 embedded processors in there. Each one is responsible for their specific tasks, right? So as you can see the picture here, one processor is designing for receiving the packet, right, from the other computation unit, deposit to our local memory, and then the other one is actually responsible for sending the packet by fetching the packet, sending to the other processing unit. And then in the middle three, there are three processors that are responsible for transfer data from the local memory, right, and to the computation unit. And then there, the central CPU is responsible for issue the instruction, right, to the AI computation unit. So this is an example how we are actually using the RISC-V processor in the embedded environment, right, to achieving the AI computation acceleration. So this Tenstorrent element is actually the basic building block for our system, right? It's become a licensable IP for us as well. So if any people actually interested in this, right, it's actually a composite element. You can form in like a 50 tera-op operation, or you can even form in a larger system like we are building here. So this scalability actually doesn't stop at the chip level, right? Like I mentioned, the second generation one-hole processor we're building, we started adding the Ethernet capability in there that actually allow you to scale to the much larger system, right? So the Ethernet system, like this is a demonstration system we're actually building today, right? So it's composed 32 of the N300 system. The board showed there, right? You can see that the black socket there is actually an Ethernet port, right? So this is actually natively connected to each other, right? So the board is actually natively connected to each other to the Ethernet port without external switches, right? And informing this 4U server, right? And achieving 12 petaflop BFA at the 6 kilowatts. So this is really a large system used for training and high performance inferencing. So the scalability coming from the architecture itself with the Tenstorrent unit, with the RISC-V processor in there, and then connect to the NOC, and then higher level, you actually connect to the Ethernet port and forming a much larger system like this, right? So we can actually natively connect to each other, right? To 30,000 of this kind of chip together without external switch. So this is very different from what the NVIDIA is proposing. So they have to go into NVLink switches, but this is natively connected. So there are a lot of talking about is RISC-V ready for high performance computing, right? So Tenstorrent actually heavily invests, from my perspective, is already ready, because if you heavily invest on the software stack, right, like us, we do in the past 6 years, right? This is a complete demonstration, the software ecosystem we have for machine learning. So you can see that we have a machine learning framework. It's been translated using the TVN to our internal operation, right? And then we actually parallelize it, and then to, based on the computation demand, and then we generate the computation graph, right? And we, based on the graph dependency, we compile and place and route and put it on the Tenstorrent, right? So we load down to the RISC-V binary, and then load down to the 5 processor you actually see there, and perform the machine learning task, right? So the whole flow is actually designed as a fully automated path, right, for all the machine learning, popular machine learning framework to optimize implementation. So you actually create a very high quality result without no manual effort, because most of the machine learning architect, right, data scientists, they're not interested in understanding what's the machine, right, what's the hardware is about, right? We also plan to do is that this solution has to be scalable as well. The same compiler should be targeted from one chip, right, even one Tenstorrent core, right, to all the many thousand of the chips, right? So this is our goal. So from my perspective, this is a very good example that you can using the RISC-V capability and then focus on with the right focus on and the investment, right, and building a complete solution for high performance computing like AI we are doing today. So changing gear a little bit. So this is our machine learning, right, AI chips, right? Changing gears that we're going to talk about the RISC-V high performance CPU processor. So you can think about the computation is actually falling into two spectrum, right? AI computation is very specific, metric multiplication, right? And then general compute is falling to the other domain. But from our observation, right, the future AI is actually going to be the combination of the both. Like for example, the GPT-3 has a lot of table lookup, right? The TV cache. So for that kind of cache lookup, it's very fragmented, right? So machine learning is actually, a theory is actually good on the computation, which is batchable, right? And can be issued can be issued together. But there are a lot of computation in the current existing machine learning framework actually require the CPU to do it because the access is fragmented, the address is fragmented, right? So the general purpose, high performance general purpose computer is actually very important for that as well. So that's why we introduced, designed this high performance RISC-V processor, right? We think this is disruptive because it's a AOI decode machine. We believe that you will be achieving projected Zen 5 performance in 2024. So this one will be, in the function-wise, we are RVA 23 profile compliance. It has an advanced branch predictor. It's an AOI decode machine, right? It's 3 low store units, 6 ALU, and then 2 branch units. And it has 2 256 vector units and 2 floating point units. So this is really a high-performance design for the data center. And then design is well under the way, right? You can see this is a PD die we demonstrated, and then we already able to boot in the Linux, so in the lab with the emulation. So we scheduled to tape out probably Q1 next year. So I just talked about what the scalability for our AI product, right? So CPU as a companion processor for the AI processor, we actually need the same kind of strategy to address the co-processor, companion processor concept. So when we design this AOI decode machine, we actually make sure that it can be, RTL can be parameterizable to supporting 6Y decode machine, 4Y decode machine, 3Y decode machine, and 2Y decode machine to ensure that we can address the market, right, with the different PPA requirement. Right. So this is easier than said than done, right, because your RTL environment need to be parameterizable. Your verification environment need to be parameterizable. So this is a very cool strategy we have. So in a very short 2 years, we actually come with the IP portfolio for high-performance superscale RISC-V processor, right? While the other company trying to achieve in 10 years. So you may ask, like, why do you need a CPU in the AI? Like I mentioned, right? So there are a lot of tasks, like, for example, virtualization, security, system management, and computation kernel setup. Those kind of management tasks you have to done by the CPU, right? So we integrate the RISC-V CPU in our black hole. That means it can do all this management tasks and by replacing the x86, right? So that means the RISC-V processor can do the general compute for maintaining the security while the AI is doing its work, doing its best work on the acceleration. Well, the other part we actually foresee is actually the AI computation in the future, like I mentioned, right, will be highly heterogeneous. Right? Only 1 minute. So it will be highly heterogeneous, and that means that there will be a lot of computation need to cooperate between the CPU and then also the GPU, right? So in this way, we actually build a processor enable them to actually have the interconnection topology and also the computation capability that they can talk to each other very easily. So we actually spend a fair amount of time to investigate that Tenstorrent overlay technology and also make sure that CPU has same topology capability like the other acceleration element in there. The processor can be also using for the network computation acceleration. I don't want to go through this, right? So we designed the CPU, we also can integrate the DPU acceleration in there, so CPU can do that for that purpose. And then in the last couple of examples, I actually just demonstrate to you, right? So how the RISC-V is being applied for in our AI processing and also for the general purpose processing and also for the future chiplet technology. So the scalability is not only coming from the computation element itself, right, but also coming from our chiplet strategy in the package level. So like we're using our ASCII Composite Building, this is really high-end, the Aegis chiplet, which contains 128 core, right, with the 4 CC NUMA quadrant in there. So it has it's local I/O coherent connect and the memory connection and the hierarchy connected through the coherent traffic. So it's actually a very high-performance CPU platform. And then we're building as a chiplet I showed there. And then this one can be composed with our AI accelerator as a heterogeneous computation platform, right? And of course, the chiplet can be using also as building a high-end server like in this. So you have DDR memory and then have I/O chip in there. So I just demonstrated that Tenstorrent has a scalable technology all the way from AI acceleration, right, computation element, right? You can use the composite chip, right? And then we can use in chip level, we can have the Ethernet port to scale out, right? And also our CPU processor family is also scalable. So with all this technology, right, we can actually address the market from the edge client, edge device to edge server, and to even the HPC in the cloud, right? So this scalable technology actually enables to address a wide range of the product we are making today. So that's why this milliwatt to megawatt actually makes sense for us, because our architecture is designed for that way. So our recent cooperation with the with the recent cooperation with the LG actually demonstrate the powerfulness of our technology. So, like I want to mention again, right, this scalability, we're using RISC-V technology to build this scalable CPU family, and then we're building the scalable AI computation element. We're using the chip there to make the scalability even higher on the package level, right? So we think Tenstorrent using the RISC-V technology, and then also machine learning technology is a unique position in this industry, right, to address such a wide range of the technology demand for the AI computation and also general compute. So that's my message. Yeah.
Thanks a lot.
Yeah.
In the interest of time, we'll be moving to the